Banach spaces is that we shall need it as a tool in proving some of the important structural theorems of Banach spaces, like the open mapping theorem, Banach-Steinhaus theorem, so on. So we shall just go into the theorem. So if X is a complete metric space, the intersection of every countable collection of dense open subsets of X is dense X. Now this is the statement. What does it mean? X is complete metric space. So we will give some notation. Let let etc. be a countable collection of dense open, that is, each Vi is open and Vi closure is okay. Then what we claim is the following. V is equal to intersection I V is not only non-empty, it's dense in X. That is V closure. Now this is the statement of the theorem. So what we start with a countable collection of dense open subsets. We are assuming that each of these VIs are open and they are dense in X. That means these properties are satisfied, and then we take the intersection and we show that this is equal to X. Okay. So let us prove this. So, okay, what do we mean by Vi is dense in X? So we have to give a meaning to this. Now, a set if for every W open in X, W intersection Y is alright. That means every open subset of X has a non-empty intersection with the particular set Y. Then you say that Y is density. This is another way of putting the density. And this is the way in which we are going to exploit, or we are going to prove this theorem. So what do we do? So suppose let W be any open set in X and W is a non-empty, because an empty set is also an open set, we are not considering. Then we show that V infinity has a non-empty intersection W. That is W intersection V non-empty. This is what we want to. Okay, so we shall proceed as follows. I'll keep the statement of the theorem there. And develop. So we introduce some notations, some useful notations. Okay. So let rho denote the metric of. Okay. So it is the distance function is rho xy. And we also define, so we write S x r to be the R neighborhood of the point x. That means the set of all y belonging to x, such that the distance from for any R positive. Okay, so we mark this one, and then S bar is the closure of SXR in in X. Now note that, see, S bar may not be the set y belonging to X I just give a very simple example. You take X to be equal to okay. Now we can certainly give an example for this. That's not difficult. Okay. For instance, you take x to be equal to infinity. Now this is complete. This is complete with the usual. Okay, now you take x equal to 1 and r equal to 2. Okay, then okay, that's not a example. Anyway, one can construct such an example. Let's spend time on it right now. Okay. Now we start with the, see, V1 is density. Therefore, this implies open W intersection V1 is non-empty. And this is also in the intersection of two open sets. Okay. Therefore, there exists an x1, r1 positive with x1 belonging to V1 such that R1 closure is contained in V1. So this is, and we can choose this R1 such that 0 is less than R1 less than. Okay, so we can make the choice of R1 in this way, because there is some R1 for which this is true. If it is already less than 1, you use that. If it is not, you choose something less than that in a way that for that this relation will be valid. Now what we work on is an induction argument. Okay. Now suppose for n greater than or equal to, we have x n minus 1 and r n minus 1 such that is contained in V n minus 1 Rn minus 2 and is contained in W intersection n minus 2. Then we have denseness of Vn. Denseness of Vn shows that Vn intersection S is non-empty. Which implies there exists Rn such is contained in Vn intersection Now we can choose the Rn in such a way that Rn is non-negative and less than 1 by n. So we started with R1 less than 1. We have Rn less than 1 by n. So you see what we are doing is we are having a situation like this. See, what we have is this, that you have, say, so you have, this is intersection Rn minus 2. Okay. Now this is non-empty, open. Okay. Therefore, what you have, you can find this is x minus 1. Now you have an xn here and an Rn such that this ball is completely contained inside. So this is the situation. This open ball is completely contained. Now this is S. This is the scenario that you, okay, and of course Rn is less than 1 by n. Now we use induction. By induction, we sequence xn such that for I greater than n, j greater than n, xi xj belong to, or what you call S. Now that means you see that the distance between xj is less than or equal to distance between which is less than 2 by. In fact, it is actually 2Rn, which is less than 2 by. So we now get a sequence which has this particular property. What does this mean? This means is a Cauchy sequence now all that you have to use is the completeness. Now use the completeness property. By the completeness of we have the sequence xn converging to some element, say x belonging to that is limit n tending to infinity of xn is equal to x. And x is of course in x. Now what more you can say? You can say that each xi Rn being a closed set. Okay. For I greater than I. Therefore, this implies x belongs to Rn, which implies x belongs to each of the beings. That means X belongs to. Therefore, we have shown that it is dense in. So that completes the proof. Okay. Now we make some remarks or a more general statement of this kind. What we do is the following. So we first define, can replace this open sets by G delta sets definition. So we will just define or recall what G delta set is. Every G delta is the intersection of countable collection of in this context you should realize that finite intersection of open sets is open. Okay, but you cannot make that statement about the countable intersection of open sets. I mean, one can easily give an example. Okay, therefore, such sets are given a new name, namely a G delta set. So this is called G delta set. Okay, now this is in the definition of the topology. And the definition of the topology, what we have is this: arbitrary union of open sets is open, but finite intersection of open sets is open. And countable or an arbitrary intersection of open sets may not be open. It's a very simple example. You take R, you take the open sets, the interval minus 1 by n to 1 by n, take intersection Vn. This is essentially the singleton set 0. This is not open. So you cannot make that statement, but this is a G delta set. Okay, therefore we give a different name for that. It's called a G delta set. Okay, now we can replace this openness with G delta. Okay, so we'll rewrite this. The statement of the theorem is this. This is a generalization. If X is complete, and G1 G2 are G delta sets, a collection of G delta sets, then in X dense in X, then intersection of GIs is a G delta. Countable intersection of G deltas is dense in X and is G delta. Okay. So first of all that we need to do is just translate this result into an application of this theorem. So what we have is that you can take Gj, you can take as intersection V Jn, n equal to 1 to t, and this is for now what happens? Now you see your statement of the theorem says the following. What does it say? Then intersection infinity Gj is the countable intersection of Gj's. This is equal to intersection of infinity. So what happens? What about this intersection? Now this is an intersection. This is a together. It's a countable intersection of open sets. Okay. Therefore, you see that, and each Vjn is dense in X. Therefore, you see that intersection J equal to 1 to Gj to it's a countable intersection of J. So you can write this Vjn. This is intersection of J equal to 1 to T. Together it's a countable intersection, as we have observed. It is countable collection of countable collections is countable. That is the argument that see, and this will become simply a countable intersection of dense open sets, which is okay, and this is also by Baire's theorem. That means, and essentially it is the countable intersection of open sets. Therefore, further. As a G dash. So that completes the proof. So in fact, you can replace this open, this part. This can be replaced by what is called a G dash. Okay, right? And then you can write the same thing, and the resulting intersection is also a G. So that completes the proof of that. Now what we look at is why this is called a category. It gives some more insight into the inner structure of space. So we will define the terms. There are sets of first category and second. So Bayes' theorem is sometimes called also known as Bayes' category theorem. Let us now define these terminologies. Okay. So okay, before we go into this aspect, we will just make some remarks. Okay. Now, if we drop some remark, drop the completeness assumption on X, the cannot be. Now it's quite easy to see. You take X to be the set of all integers. Okay. You take X to be Z. Okay. And then you you can write this as the union of okay. Now each of this is an open set. The open set in the sense that it is a relative open subset. Now suppose we drop this completeness assumption because we don't have a completeness of this space, right? And therefore we can see that if you take a countable collection of open subsets of X, this intersection is not necessarily dense in X. Because you see that if you take any subset, it is not dense. And in fact, can even you take all open sets. For instance, you take what is called, right? Take this is a closed subset of set. Take its common. Okay, then it is open. So you take the intersection. What will happen? You see that this is M. Okay, we'll do a example in a different. We give the following example. Take X to be a set of ratios. Now this you write as, because this is a countable connection. You can enumerate them. Okay. Now rho is the usual matrix. Okay. Now we write Dm to be the complement of each Q. That is A complement is this is what we do. So this is the notation. Now this you define for etc. Then you see that Dm closure equal to, right? And Dm is, so this is dense in Q, whereas this is also true. And therefore you take the intersection complement, and this is, that's very easy to see, it is empty. Okay. Now we look at some examples. And then after that we come to this why it is called a category. Okay. One more result that is worth to suppose so we can this we have already proved. While proving this result, so we'll just write it out. If X is a metric space, then the intersection of a finite number of dense open subsets is one. Now this we have proved. So what we have done is essentially it's a metric space, but we are not assuming X is complete. So that is one thing. We are not assuming X is complete. So what we can conclude is that the conclusion has to be changed then to a finite intersection instead of a countable Now here you go to the proof of the Bayes theorem. The proof of the Bayes theorem, suppose you terminate at some intermediate stage, say a finite stage, okay, then you get a finite sequence. See, this is a finite sequence that you are constructing, okay, and they are all there in that set. Whereas you cannot use completeness to get a limit in that case, okay, right? Therefore, the moment you drop completeness of X, we cannot assure that the sequence that you construct is you can go till the end and show that this sequence there exists a Cauchy sequence, but its limit, the existence of the limit of the Cauchy sequence is not assured. Okay, and we have already seen an example what happens in this case, right? We have already explored an example, right? So this is a finite intersection instead of a countable intersection. And then what we can prove is that X is a non-empty and dense in X. Okay? That is immediate. Okay. So it would follow that at each stage when you work on this is there you are getting dense subsets which are non-empty. Okay. So at finite level, through a finite number of steps, you keep getting non-empty dense subsets, open subsets. But you know that eventually, or say non-empty and dense, and eventually you see that this is not. You cannot prove that the intersection, the countable intersection, is empty, and we have already seen some. Now we look at some. Now we use the alternative version of the Bayes theorem. Okay. Now we also make a remark. In a non-complete metric space, this is what we have proved. The intersection of a countable collection of equality. This we have already seen the example. Okay. Now we go into the statement that why it is called a category. I think I will stop this talk at this stage and then do a very short talk connects this. Thank you very much.